So far we have been discussing momentum transfer correlations first, and then heat and mass transfer correlations for different configurations, flow through pipes and channels, flow past a flat plate, flow around a particle, and flow through a packed column filled with particles, for example. In this lecture we will consider the phenomenon of natural convection. If I have an object, okay, with some characteristic distance L c, okay, with temperature T is equal to T naught at the surface, placed in a fluid with T is equal to T infinity far away, okay, the object is hotter than the fluid. Okay. Then of course, there will be diffusion which takes place, so that the heat travels from the object to the fluid surrounding the object. There is a second mechanism which is convective transport due to the heating of the fluid close to the object. The fluid close to the object is hotter, and hotter fluid usually has a lower density. Therefore, this hotter fluid will rise because the density is lower. Okay. And as this hotter fluid rises, it will carry along the heat energy with it. Okay. And as the hotter fluid rises, obviously in order to fill in the vacant space, colder fluid has to come in, okay, from the ambient at temperature T infinity. Okay. And this colder fluid replaces the hotter fluid, gets heated up and rises in turn. Okay. And the rising and the driving force for this convection is the buoyancy force due to the temperature difference between the hot object and the ambient fluid. That is why it is called natural convection, as compared to the previous examples where we had studied, which were all what are called forced convection. That is, you are forcing the flow by some external agent to sweep past the object or through the pipe. Okay. So, therefore, that is a forced convection problem. This is natural convection because the temperature difference automatically causes a decrease in density, buoyancy force in the presence of gravity, and that in turn causes convection. That is, the velocity field created by the temperature difference carries with it the heat, and therefore, you have convective transport of heat. So, in this case, the driving force for natural convection is the difference in density between the fluid close to the surface and the fluid far away. Okay. So, the force per unit area, okay, gravitational, okay, or buoyancy, force per unit volume. The force due to buoyancy per unit volume is equal to the difference in density times the acceleration. Mass times acceleration is force, and density times acceleration is the force per unit volume. So, this is the buoyancy force per unit volume. Okay. This delta rho is related to the temperature difference, okay, between the two. Okay. Usually, for if the range of temperatures is not too large, we can write delta rho is equal to rho beta delta T, okay, where rho is equal to the average density and beta is what is called the thermal expansion coefficient. This has dimensions of degrees centigrade inverse or Kelvin inverse, and delta T is equal to the temperature difference. okay, delta T is equal to the temperature difference. Okay. So, this causes a velocity. How do we estimate the velocity? Okay. The velocity has to be balanced either by the inertial force density or the viscous force density. Okay. So, we have to balance the buoyancy force density with either the inertial force density or the viscous force density. Okay. As we had seen in the very early on in the settling of a sphere, at low Reynolds number you would balance it by viscous force density because viscosity is dominant. At high Reynolds number you will balance it by the inertial force density because inertia is dominant in that case. In this case we will consider the inertial force density and I will come and justify that a little later. Okay. So, what is the inertial force density? Okay. This has to be equal to the density times the characteristic velocity square divided by the characteristic length. Okay. You can see that this has the same the same dimension as a force density, mass per unit length per unit time. Okay. Force density is the force per unit volume. So, it is mass per length power minus 2 and T inverse. Okay. And it has the same dimension as this buoyancy force density, where LC is the characteristic length. This is the dimension of the object, and VC we do not yet know. We will estimate VC by balancing the two. Okay, that is that rho VC square by LC is equal to rho G beta delta T, okay, which implies that Vc is equal to root of G beta delta T into the characteristic length. Okay. So, this is an estimate of the velocity that is generated, okay, due to this buoyancy effect by balancing out the inertial force density with the buoyancy force density. Okay. Now, we can express this. Now, we have the velocity scale. We can then determine the ratio of inertial and viscous effects for this particular velocity scale and length scale. Okay. So, the Reynolds number for this case is going to be equal to rho Vc Lc by mu. Which is equal to rho Vc Lc root of G beta delta T Lc by mu. This is what you would get for the definition of a Reynolds number based upon the characteristic velocity generated by the gravitational force density or the buoyancy force density. Usually what is the conventional definition is the square of this Reynolds number is written as the Grashof number, okay, which is rho square G beta delta T Lc cubed by mu square. Okay, that is the Grashof number. Conventionally, it is the square of the Reynolds number that is used as the independent dimensionless parameter in this case. So, this is a ratio of inertia and viscosity for this case, and the other independent dimensionless number is the Prandtl number. Okay. Okay. So, this Reynolds number square can also be written as G beta delta T Lc cubed by nu square. Nu is ratio of viscosity and density, mu by rho, or the Prandtl number is written as nu by alpha. Okay. So, these are the independent dimensionless parameters. The dependent dimensionless parameter is of course the Nusselt number, Okay. Nusselt number is defined as Q average by K delta T by LC. Okay. That is the definition of the Nusselt number. And the correlations of the form Nusselt number is a function of the Grashof number and the Prandtl number. Okay. The other dimensionless group that is sometimes used is the Rayleigh number, okay, which is G beta delta T LC cubed by mu alpha. So, the Grashof number times nu by alpha. So, the Grashof number times the Prandtl number. Okay. So, these are the independent dimensionless groups. The Reynolds number or its square, the Grashof number, or the Rayleigh number and the Prandtl number for this natural convection problem, and the dependent dimensionless parameter is the Nusselt number, okay, for this case. So, let us estimate the Grashof number for some simple situations. Okay. So, let me take the example of the human body itself. Okay. The average meters square and 0.1 meter cubed. These are it is highly non-spherical, as you well know. Okay. So, the surface area is about 2 meters square and the volume is about 1 meter cubed. Okay. What is the equivalent diameter? Okay. And then characteristic velocity for natural convection in air if body temperature is 37 degrees centigrade and ambient is 25 degrees centigrade. Okay. And the properties are given. The density of air is equal to 1.25 kg per meter cubed. Viscosity is equal to 1.85 into 10 power minus 5 kg per meter per second. Okay. Thermal conductivity is equal to 2.62 into 10 power minus 2 watts per meter per degree centigrade. Cp is equal to 10 power 3 joules per kg per degree centigrade, and the thermal expansion coefficient in air is 3.43 into 10 power minus 3 degrees centigrade to the whole inverse. Okay. So, these are the properties. Okay. So, how do we estimate the characteristic velocity? We know that the characteristic velocity is equal to root of g beta delta t LC. Okay. Characteristic length in this case will be the equivalent diameter of the human body. dE is equal to 6 times the volume by the surface area. Okay. That is 6 into 0.1 meter cubed is the volume, divided by 2. Okay. Meter square is the surface area. Okay. This is 0.3 meters. Okay. This is 0.3 meters. Therefore, Vc will be equal to square root of 10 meters per second square into 3.43 into 10 power minus 3 degrees centigrade whole inverse into delta T 37 degrees minus 25 degrees into into 12 degrees centigrade into 0.3 meters. Okay. And you can calculate this, it turns out to be about 0.35 meters per second. Okay. So, natural convection velocity around our body is actually 35 centimeters per second even at rest, just because of the temperature difference between the body and the ambient fluid. Our body is at about 37 degrees centigrade. The air around us is approximately at 25 degrees centigrade at standard temperature and pressure. What is the Grashof number? Okay. Rho square g beta delta T LC cubed by mu square. Okay. Density is 1.25 kg per meter cubed, the whole square. Gravitational acceleration is 10 meters per second square. Beta is equal to 3.43 into 10 power minus 3, okay, degrees centigrade the whole square. Okay. Into delta T is 12 degrees centigrade. Okay. Into L cubed, that is 0.3 meters the whole cubed. Okay. The whole thing divided by the viscosity square, 1.85 into 10 power minus 5. Okay. 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 And you can verify that this turns out to be dimensionless. The actual value of this is 5 into 10 power 7, okay, 5 into 10 power 7. Okay. Note that the Grashof number is the square of the Reynolds number. Okay. So, if you calculate the Reynolds number in this case, that will turn out to be approximately 7 into 10 power 3, 7,000 or so. Okay. The square of that is this, which is the Grashof number. So, as you can see, even in this typical situation, the Grashof number is large. Okay, the Grashof number is very large, and that justifies our using the inertial force density in order to calculate the characteristic velocity. Okay. So, this is the Grashof number, and the Prandtl number will be equal to Cp mu by k. Cp is 10 power 3 joules per kg per degree centigrade into 1.85 into 10 power minus 5 kg per meter per second, divided by the thermal conductivity, which is 2.62 into 10 power minus 2 watts per meter per degree centigrade. and you can once again verify that this will turn out to be dimensionless, and the value of this is about 0.71. Okay. So, typically for normal situations in air, the Grashof number is almost always a very large number, okay. And therefore, this transport takes place basically at high Grashof number or high Reynolds number, okay, natural convection. Even for modest temperature variations of about 10 degrees or so, the Grashof number is actually very large. What about transport in liquids? Okay, so, let us look at a typical situation for transport in a liquid. Okay. Characteristic velocity and Grashof number for natural convection into water from a horizontal cylinder of diameter 1 centimeters, heated to 35 degrees centigrade in ambient water. At 25 degrees centigrade. Okay. For water, rho is equal to 10 power 3 kg per meter cubed. Mu is equal to 10 power minus 3 kg per meter per second. Okay. Cp is equal to 4.2 okay. The thermal conductivity is equal to 0.6 watts per degree centigrade, and beta thermal conductivity is 2 into 10 power minus 4. Degrees centigrade the whole inverse. Okay. So, these are the properties, okay, and we have to calculate the characteristic velocity, the Grashof number, and so on. Okay. So, let us do that. The characteristic diameter in this case is just equal to 1 centimeter, is equal to 0.01 meters. Okay. The characteristic velocity is equal to rho g beta delta t LC square root of. Okay. My apologies, this should be inverse, please correct that. Degree centigrade inverse. The temperature difference was 10 degrees centigrade. Okay. Cylinder was at 35, ambient at 25. So, this is 10 degrees centigrade. Okay. Into the characteristic length is 0.01 meters. Okay. So, if I multiply all of this, I will get 1.4 into 10 power minus 2 okay, meters per second. Okay, that is the characteristic velocity. 1.4 centimeters per second is the velocity, characteristic velocity of the flow in this case. Okay. The Grashof number is equal to rho square g beta delta t Lc cubed is equal to 10 power 3 kg per meter cubed whole square. To g is 10 meters per second square. Beta is 2 into 10 power minus 4 degrees centigrade whole inverse. Delta T is 10 degrees centigrade into Lc cubed is 0.01 meters the whole square, whole cubed, Lc cubed, okay. Whole divided by viscosity square, which is 10 power minus 3 kg per meter per second whole square. This is the Grashof number, okay. And you can easily do this calculation, and the final result you get will be 2 into 10 power minus 4, 2 into 10 power plus 4, which is once again much larger than 1, okay. So, that was the reason once again, even for this modest temperature difference around a small object, the Grashof number is still large compared to 1, and that is the reason we had used the inertial force density to balance the buoyancy force density when we calculated the characteristic velocity. That is justified by our calculation, which shows that the Grashof number is large, okay. The Prandtl number, okay, is equal to Cp mu by k is equal to 4.2 into 10 power 3 joules per kg per degree centigrade into the viscosity, which is 10 power minus 3. Okay, kg per meter per second divided by the thermal conductivity 0.6 watt per meter per degree centigrade. This once again you can verify is dimensionless. The end result you get will be 7. Okay. So, Grashof number is almost always large, Prandtl number is almost always order 1, okay, for these kinds of natural convection problems. Okay. So, the correlations are also written in this regime for large Grashof number and for Prandtl number over a range of values from small to large for the laminar regime. Okay. So, the Nusselt number correlation is usually of the form Grashof number power 1/4 times some function of Prandtl number. Okay. In all cases, in the limit of large Grashof number for a laminar flow, the Nusselt number is proportional to Grashof number to the 1/4 power times some function of the Reynolds number. Okay. Note that Grashof number is the square of the Reynolds number inertial to viscous effects. Prandtl number is equal to momentum diffusivity by thermal diffusivity. That is the Prandtl number is momentum diffusivity divided by thermal diffusivity. Okay. So, you can get more specific forms of the correlations in the two limits. Prandtl number much larger than 1, it can be shown that Nusselt number is equal to some constant, okay, Grashof number power 1/4, Prandtl number power 1/4, and for Prandtl number much smaller than 1, Nusselt number is equal to some constant Grashof power 1/4, Prandtl power half. Okay. This can be derived analytically. Okay. The Grashof number power 1/4 dependence is the same in all cases. Okay. And I should note that in the limit of high Grashof number, the assumption is that there is close to the surface a thin boundary layer within which all of the flow upward is happening. Okay. So, this assumes that at high Reynolds number, any heat that is being generated by the particle immediately gets swept downstream, so that the temperature disturbance due to the particle is restricted to a thin region close to the surface, and the thickness of this region goes as Grashof number power minus 1/4, in the limit where the Grashof number is large or where convection is much larger than diffusion. Okay. So, this generally works for these two correlations. Okay. They generally work for Grashof number in the range 10 power 4 less than Grashof number less than 10 power 9 or so. Okay. This is the regime where there is a laminar flow, okay, around the particle, okay, and the flow becomes turbulent for Grashof number greater than about 10 power 9. Okay. And where the particle flow becomes turbulent, then these correlations are no longer valid. Okay. So, this in brief is a summary of the natural convection. The natural convection is generated by a buoyancy force upwards because the fluid close to a heated surface has a higher temperature in compared to the ambient fluid. Due to this, the temperature fluid close to the surface rises, and as it rises it carries along the heat with it, and the fluid from the ambient comes inward to replace the fluid that has risen, and this creates a heat transfer rate which is much higher than what you would have by diffusion. Characteristic velocity we had estimated by balancing the buoyancy force density and the inertial force density. Based upon that, the square of the Reynolds number is the Grashof number, Prandtl number, ratio of momentum and thermal diffusivity, and the Nusselt number is the dependent variable. We saw that in most cases the velocity varies between about a centimeter per second to about tens of centimeters per second. In gases it is tens of centimeters per second. In liquids, for a modest temperature difference of 10 degrees it is about a centimeter per second or more. Grashof number varies in the range 10 power 5 to 10 power 7 in all of these cases. Prandtl number over range less than 1 to greater than 1. Okay. And based upon that, the correlations are Nusselt number is Grashof power 1/4 times some function of Prandtl number, and I had given you specific forms in the specific regimes. So, we will complete our discussion of natural convection, and I will start discussing diffusion and dispersion in the next lecture. I will see you then.